Wednesday, right? Try to get here a little bit early, as I will do the same. We'll get the exams passed out so you can start right at 2:20. Make sure you bring a Scantron 882, erasers, your calculator, and if you wish, your 3" by 5" index card. Remember, it has to be an actual index card. It can't be a piece of paper cut out to that size. Okay, just index card. It has to be 3" by 5", nothing bigger. But those are the only criteria. You can put anything on it that you want to. You can use any size font, as long as you can read it with your unaided eye. So what we'll be doing today is covering material, right, that's not on that exam. We'll be finishing up Chapter 8 today and probably starting into Chapter 9. What we learned last week on Wednesday was how to predict the geometry, the electron group geometry and the molecular geometry, the shape of some simple molecules. And basically, all we had to do was draw the Lewis structure, look at the central atom, figure out how many electron groups are attached to that central atom. Remember, an electron group can be either a lone pair of electrons or a bond. And just keep in mind, because one of the things that tricks people at first is it doesn't matter if it's a single, double, or triple bond. That bond only counts as one electron group, right? So a double bond's not two groups, it's just one group. But count the number of electron groups, and right away, that'll tell you the electron group geometry. It's going to be the basic shape, the VESPR shape that minimizes the interactions between those electron groups. Linear, trigonal planar, tetrahedral, trigonal bipyramidal, or octahedral. Those are the electron group geometries. Then, to get the molecular geometry, the shape, remember all you have to do is you have to look at the central atom, see how many of those electron groups are lone pairs of electrons. Because even though the lone pair is there and they affect the other electron groups, we can't see it. So we pretend like we don't see it. And so it affects the shape, but it's not part of the molecular geometry. And from there, we had to figure out where that went. But really, all it comes down to is Lewis structure. Make sure you get the best Lewis structure. Count the electron groups. Count how many lone pairs there are in that central atom. And from there, if you know that table, if you have it on your card, then you can figure everything else out. What we're going to do now is go and add on to that. Now that you know, you can predict what the shape of a molecule is, we can predict whether or not that molecule is polar or not. We introduced this at the end of last chapter, the end of Chapter 7, when we talked about electronegativities and electronegativity differences. Remember, we talked about some simple molecules. We didn't know about geometries yet, but we were able to talk about how, for instance, the water molecule is polar because the dipoles don't cancel out to that sun. Familiar at all? Yeah, a little bit. Remember, what we said was what I had said at that time was you don't know why yet, but the water molecule is bent, the shape is bent. Now you guys know why, right? So if we were to look at this using VESPR theory, how many electron groups are on the central oxygen atom? 4, right? So what's the electron group geometry? Tetrahedral, right? 4 electron groups is tetrahedral. There are 2 lone pairs, right? That's a pair, that's a pair. So if there's 4 electron groups, 2 of them are lone pairs, that's AX2, E2. That's the molecular class, right? What's the molecular geometry? Bent, right? And that's how we knew that it's bent. So what that means is, okay, these are coming down in front of an angle like that. What do you think the angle is here?
Less than 109.5.
Good, a little bit less than 109.5, right? We also know that oxygen is more electronegative than hydrogen. There's that table, and I believe it's in Chapter 7, that gives you the electronegativities of the elements on the Pauling scale. Look it up. I think hydrogen's like 2.1, Oxygen's around 3, something like that. There's a difference of about 0.9 electronegativities, which means that the electron density is being shifted up towards the oxygen. Remember, the convention that the textbook uses and that we're going to use is that the arrows point towards where the electrons are being pulled away from, and the tail is where the electrons are being pulled towards. Okay? That's the opposite of what you probably saw in your 142 text or wherever you had chemistry before. But that's actually the IUPAC convention, and that's what your book uses. That's what we'll do. So what this means is that there's some electron density shift up here and away from the hydrogens, which means that there's a partial positive charge there, negative here. There's a net dipole moment. Probably looks something like this. Where the blue arrow is showing the result of all of the interactions of the atoms pulling the electrons in the bonds, in the molecule. So overall, the result is that somewhere down in this region, there's a resultant positive charge and a negative charge somewhere up here. It's a polar molecule. And it's not much different in 3 dimensions than it is on the board. The way these shapes are set up, the angle here is 109.5, so in water it would be a little bit less than this. But this would be the oxygen, these would be the hydrogens. The oxygens pulling the electron density in these bonds away from the hydrogens. The result is that there's a negative charge here, positive charge down here. It's a polar molecule. On the other hand, look at this molecule here, carbon tetrafluoride. What we want to do, our goal here, is to predict whether or not the molecule is polar or not. And the way we're going to do that is we're going to draw the Lewis structure, get the geometry, the molecular geometry, and then look at the bonds, see if they cancel, if there are any polar bonds, whether or not they can cancel each other out. So the Lewis structure for this, carbon is in the center, 4 fluorine atoms. How many valence electrons total do we have? 32. 32. We use those 8 to form the bonds for the peripheral atoms. 24 left. Each fluorine needs 6 more electrons. Times 4 is 24. That's how many we have. Put it in. The octet rule satisfied. The formal charge on each of the fluorines is 0. The formal charge on the carbon is 0. That's the best we're going to do. So now that we have the Lewis structure, what's the molecular geometry? Well, okay, what's the electron group geometry? Tetrahedral, right? You guys, everybody sees there are 4 electron groups on the central atom. None of them are lone pairs, so the molecular geometry is what? Also tetrahedral, right? If there aren't any lone pairs, then the molecular geometry and the electron group geometry are the same. So it looks like this. In in that table, in your textbook, the electronegativity of fluorine is 3.98, basically 4. Carbon is, I think, around 2.4. So the difference in electronegativity is around 1.6, somewhere in that neighborhood. What kind of bond is it making? Remember how we classified the bonds?
Polar covalent.
Polar covalent, right? There's covalent, polar covalent, and ionic, right? Depending upon the difference in electronegativities. So this is a polar bond. And so this is what the molecule looks like. Fluorine, 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 carbon, right? So each of these bonds, difference in electronegativity of about 1.6. And so this fluorine is pulling the electrons towards it, as are all of these, right? The result, though, the overall net result, is that all of these pulls cancel. There's no net resultant dipole moment. It's a symmetric molecule. And so it's nonpolar. Can you guys see that from looking at this shape? Yes? Okay. Same idea. You want to figure out whether or not this molecule is polar or not polar. When I draw the Lewis structure, you get this. I'm going to make that fluorine. Change the bromines to fluorines, please. So there's no doubt. All right. Still, everything's tetrahedral, right? Electron group geometry, molecular geometry. What do you guys think? Is this a polar molecule or non-polar? Polar. Everybody agree?
Yes.
It's polar. What? Okay. Sometimes when you get in a hurry, people look at the two-dimensional drawing, and it looks like these fluorines are canceling each other out, right? And the hydrogens are canceling each other out. But if you look at the three-dimensional structure, the tetrahedral geometry, the reds will be the fluorines, let's say. There's no way I can put these in a tetrahedral geometry to where they're going to cancel out each other. Right? This is kind of without the hydrogens kind of looks like water, right? See that it doesn't cancel. These don't cancel. These are different than these. They don't cancel. Doesn't matter where I put them. Right? There's nowhere I can arrange these to where it's not going to be like that. So polar. You guys don't buy that? Trigonoplanar. So what we're looking for here, okay, there's two conditions that a molecule has to meet for it to be a polar molecule. In order to be polar, the molecule has to, one, have some polar covalent bonds in it. Difference in electronegativity greater than about 0.4. And there has to be some asymmetry in it. There has to be some asymmetry so that the poles don't cancel out. So if the molecular geometry is trigonal planar and the atoms are all identical, that's not going to be polar, right? Because they all cancel out. You guys see that? If one of the atoms is different than the other two, then as long as there's at least one polar covalent bond, then it'll be a polar molecule. That's trigonal planar. We've done tetrahedral already. Trigonal bipyramidal. So if they're all the same, then of course it would be nonpolar. One of them's different. What do you think?
Polar.
Doesn't look symmetric, right? There's this asymmetry up here. Different poles on the electrons. Again, as long as there's at least one polar bond, then this will be a polar molecule. What about two?
Non-polar.
What do you think? Josh says non-polar. You guys agree? Polar? Here's some polar up there. Well, what's that? Yeah, assume that there's at least a polar bond, yeah. Depends where I put it, right?
Yeah, I was going to
Right?
say.
There's two. Remember, in trigonal bipyramidal, there's the axial position and there's the equatorial positions, which are different from each other, right? So if I put this one right here, then it's going to be nonpolar, right? That's a nonpolar molecule. You guys see that? On the other hand, if it goes in the equatorial position, that's not going to cancel, is it? So that would be a polar molecule. We're going to talk about, by the way, the relationship between those two compounds. Those are different compounds. They're called stereoisomers of each other. We're going to talk about that relationship in a minute. But, so it depends, right? And from then on, it depends, really. Well, actually, the next one, if I have three, I don't have. Let's see. What about three?
Has to be polar.
Let me ask you this. Okay, so if I put it here, that looks like it's going to be polar, right? Sure. If I pick one of these two, it still looks polar, right? Is there any way I can make it non-polar?
If you put all
All equatorial, right? So, it depends. There. That looks nonpolar, right? That's like the one where I had the two red ones here. It's the same thing, really. So octahedral. Again, if they're all the same, no matter what, it's nonpolar. All right, so nonpolar. If I replace one, what do you think? As long as there's at least one polar bond, then it'll be polar, right? And then from there it depends, just like it did with the trigonal bipyramidal geometry. If I put the second atom, opposite, then it'll be nonpolar. If I put it here, it'll be polar. So. Tetrahedral again. What if there's a lone pair there? Be polar, right? As long as there's a polar bond. This could represent, for example, ammonia. Do a structure like this. So, what's the electron group geometry for ammonia? Tetrahedral. What's the molecular geometry? What is it? Trigonal pyramidal, right? Yeah. So this is trigonal pyramidal. There's a difference in electronegativity between nitrogen and hydrogen. Now, nitrogen's about 2.5, hydrogen's about 2.1. It's about 0.4, but it's enough to where these are polar bonds, so it's going to be a polar molecule because it's not symmetrical. Let's see. What about the trigonal bipyramidal electron group geometry? Remember where the first lone pair goes? You have a lone pair? No, no. Anybody remember? Where? Equatorial, right? Yeah, the sides, right? Remember that, right? Because that'll help you, if you're not sure what your shapes are. Trigonal bipyramidal, you put all the lone pairs in the equatorial positions. Remember I explained why that was? Because they're further away from each other. Remember that? Lone pair interactions are stronger than lone pair bond pair, which is stronger than bond pair. What's this molecular geometry called?
Seesaw.
Seesaw, right? Assuming those are polar bonds, does that look polar or non-polar to you?
Polar.
It does. It looks polar to me too, right? These might cancel with each other, but this is kind of like water. That's not going to cancel out. You guys see that? Polar. Next lone pair, what's that called? T-shape. Polar or non-polar. Assuming there's a polar bond at least. Polar, right? Octahedral. Doesn't matter where the first lone pair goes in the octahedral, all the positions are the same. What's this called? Square pyramidal, right? Again, assuming at least that they're polar bonds, polar or non-polar?
Polar.
Polar, right. Where does the next lone pair go? Yeah. Polar or non-polar? do you think?
None.
Non-polar, right? It looks pretty symmetric to me, doesn't it? Square. This cancels with this with this. Again, as long as they're all the same atom. If you change it, if one of these is different, now it's non-polar, right? I mean polar. And if there's two different ones, then it depends where they are. If they're opposite, then it's non-polar. If they're here and here, then it's polar. See how that goes? So now you can predict whether or not at least any of these simple shapes are polar or non-polar. Next, isomers, stereoisomers. Coming back to, let's go back to the octahedral geometry. For instance, sulfur hexafluoride. Starting with that. Sulfur hexafluoride, octahedral molecular geometry, non-polar. If we replace two of these with, say, chlorines, look like that. Then, as you guys noted before, this would be polar, right? Whereas if the chlorines were here and here, it would be non-polar. What that means is that those are two different molecules, depending upon where those chlorines are attached relative to each other. What we're talking about here are isomers. Isomers have the same formula as each other, but different order of attachment of the atoms. This is section 8.10. There are different kinds of isomers. Constitutional or structural. Geometric. I'll explain what each of these types are. But there are constitutional isomers and there are geometric isomers. And a specific type of geometric isomer is called a stereoisomer. Both of these molecules have the formula C2H6O. Two carbons, 6 hydrogens, and 1 oxygen. 2 carbons, 6 hydrogens, 1 oxygen. What makes them different is the order of attachment of the atoms. In the top one, in dimethyl ether, you don't have to know these names, by the way. We have, each of the carbons is the same as each other. They each have 3 hydrogens attached, and there's an oxygen linking the two carbons. Whereas here, 2 carbons are attached directly to each other. One's terminal has 3 hydrogens, the other's internal has 2 hydrogens, and then it has the oxygen with the hydrogen on the outside. Same formula, different structure, different properties, right? This, this is the stuff in beer and wine and all that. This, if you drank, it would kill you. Not good. No. Yeah, probably. So that's what constitutional or structural isomers are. Geometric isomers are like this. I'll have another off the heat. Here, it's the same formula, right? SF4Cl2. Really the same order of attachment, right? There's 1 sulfur in the middle with 4 fluorines on it, 2 chlorines, right? But geometrically, the 2 isomers are different from each other because in this one, right, they're 90 degrees apart basically, and in this one they're 180 degrees. They have different properties, right? You guys already told me that this one's non-polar, the other one is polar. Those are different properties, right? So they're different substances. And the relationship is they're geometric isomers of each other. Stereoisomers. Show these. Talk a little bit about these. What stereoisomers are, they're geometric isomers, meaning that the order of attachment is the same, but the arrangement is different of how they're attached to the central atom. And on top of that, they're what are called non-superimposable mirror images. The most obvious non-superimposable image probably are your hands, right? Take this, if I were to take my left hand, hold it up to a mirror, it would look like I'm looking at my right hand, right? You guys see that? So these are mirror images of each other. But they're non-superimposable, meaning I can't make everything line up. Here the palms are, they're facing the opposite directions, right? If I want the palms facing in the same direction, now my fingers don't line up anymore. You guys see that? So your hands are non-superimposable mirror images, stereoisomers. Well, they're said to be chiral. They have a When you guys get into organic chemistry, you're going to have to deal with stereoisomers a lot more than we are here. This is just a basic introduction. But if you see it here, it'll make it a lot easier, I think, when you get there. I'm going to build the mirror image of this molecule right here. What's important here is that there are 4 different groups attached to the same atom. Right? That's what we mean by a chirality center, a chiral center. Mirror images, right? These could be any groups, any different groups. You know, for example, this molecule might be bromochlorofluoromethyl. They're non-superimposable because no matter how I line them up, they're not going to match. See, the blue and the whites don't line up. The orange and the red does, right? So I try to line up the blue and the white. Now the orange and the red don't line up. You see that? These molecules they're stereoisomers of each other. They're non-superimposable mirror images. And most stereoisomers, molecules that are stereoisomers of each other, have similar chemical reactivities. They undergo most of the same chemical reactions. But it ends up that there are some mechanisms, particularly in biochemistry, where the stereochemistry is important. Right? Carbone, it's a molecule, and there's one of the stereoisomers, and it has a stereoisomer, L-carbone and D-carbone. One of them smells like caraway seeds, the other smells like spearmint oil. And the only thing that's different is that there's a chiral center, right? And one is one way, the other is the other way. And when that molecule docks in your nose and causes you to smell it, one of those stereoisomers docks in one place, causes you to smell one thing, and another docks in another place, causes you to smell something else. There's amino acids have chiral centers in them, right? And it ends up, it's pretty important that what their chirality is. So, okay, after all that, what are you going to have to do at this point? Be able to tell whether or not a molecule has a chirality center and consequently a potential stereoisomer. And all you're looking for are 4 different groups attached to the same atom. For this class, that's all you need to look for. I believe there's a sapling homework problem, or maybe it's a problem in the text that asks you to do that. So that's what you're looking for, 4 different groups. And that brings us to the end of chapter 8. Any questions on any of that stuff? So what I'm going to do now is start a little bit of chapter 9.
Did you go with the Constitution?
Yes, that was the ethanol and the dimethyl. What's that? Yeah, it's different order of attachment. Whereas geometric isomers have the same order of attachment with different geometry. Chapter 9, okay, what are we talking about here? Are basically two different theories of bonding. Molecular orbital theory, hybridization theory. They want $300 for a set of those, do you know that? Styrofoam balls.
Get some Legos.
Like, yeah, right?
That's what Legos are.
What?
I got Legos at work.
You need the right angles, right? You need the 109.5, the 120, and all that. Still.
We're always better on Legos than I was.
So what we're trying, okay, so So before we go on, do you guys understand what you're expected to be able to do with what we were just talking about? Be able to predict whether or not a molecule is polar or not? Okay. Be able to determine the relationship between the two molecules. Are they constitutional isomers of each other? Are they geometric isomers of each other? Are they stereoisomers of each other? Right? Or does a molecule have a chiral center? Is it a chiral molecule? If it is, that has 4 different groups attached to the same atom, that means it has a stereoisomer possibly.
Can you explain again what's the difference between the stereo, not stereo, the chiral, the first one, the constitutional?
Constitutional? Yeah. In short, constitutional isomers have the same formula but different order of attachment. I like the two that I showed, the dimethyl ether. And the ethanol. The atoms are arranged differently. They're different compounds. They have the same formula. And they're constitutional. Whereas geometric isomers, they have the same order of attachment, but the geometric arrangement is different. The angle between the substituent groups is different, the geometry. Like in the sulfur tetrafluoride dichloride, which is SF4Cl6, you could have 2 different compounds. Either the chlorines were 90 degrees from each other, or they were 180 degrees from each other. That's not a constitutional isomer because it's the same order of attachment. There's still a sulfur in the middle, 4 chlorines and 2 chlorines attached to it. Right? But there's potential for 2 different geometric arrangements, 90 degrees or 180 degrees. Rest of you guys okay with that?
Can you explain the chiral?
Chiral? Sure. Okay. There's a lot going on with chiral compounds, but the basic thing that you need to be able to do is look at a molecule and look at the formula for a molecule and determine whether or not it has a chiral center, if it's a chirality center, if it's a chiral molecule. And the way you do that is you just see if there's any atom in that molecule that has 4 different groups attached to it. If there are, then that's a chirality center, and it's a chiral molecule, which means it could have a stereoisomer.
So it's very easy to spot, right? And it has 3
What's
different.
that?
Is there such thing as having 3 different attached? That would be something else, right?
That wouldn't be a stereoisomer. That would be, yeah. All we care about is 4.
Four.
If there's 4 different groups, and they can be different weight on down the line. As long as there's even one little difference between them, then they're different groups, and that's a chirality center. So that's the basic thing that you have to know about chiral compounds. I'm going to give an example of that. Looks complicated, right? But the D stands for deuterium, the T stands for tritium. They're isotopes of hydrogen. Deuterium has an extra neutron, tritium has 2 extra neutrons. This carbon right here has 4 different groups attached to it. And that makes it a chirality center. Only has a carbon, 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 right? And that carbon has 2 hydrogens, 2 and 2. Then there's another carbon outside that, right? You see that? That's all the same. But then when you finally get out here, this carbon has a fluorine on it, none of the others do. This has a deuterium on it, none of the others do, and so on. Right? There's one little difference way out here, 4 different groups. That's a chiral center.
Each carbon you consider chiral center?
Well, let's see. Does this carbon have 4 different groups attached to it? Is it? See these 2 hydrogens? They're the same, right? So no, that's not. This one? No, because it has 2 hydrogens. See, the thing is, once you find 2 identical things attached to that atom, you can say it's not a chirality center. So that's not. That's the only chiral center there. But it's certainly possible to have more than one chiral center in a compound. That's possible.
How does that look as a formula?
What's that?
As a formula, how does it look?
The formula
Yeah.
for this? I don't know.
Oh,
6, 7, 8, 9. There, let me.
it's okay. I get it. That's what I'm confused.
C9, H, many, right? 4, 8, 12, 16, right?
Oh, okay.
Oh, then the others. There's 2, 4, 6, 8. Actually, it's 24, right? No, that's 16. That's it.
All right.
Something like
Yeah.
that. But that's really, at this point, all you have to do is look for 4 different groups. Any difference makes them different. And that's
Yeah.
what I would say.
So it could be like carbon, 3, hydrogen, 4, and then like 4 other different ones, and that's already a chirality, whatever you call it.
Chiral center.
Chiral.
You have to be careful. You have to draw the structure. You
Oh,
can't.
okay.
Okay. Don't try to tell just from the formula
Oh.
whether or not that's a chiral compound. You have to draw the Lewis structure. You don't need the 3D molecule necessarily, but you have to draw the Lewis structure.
Okay.
Any other questions on your next one? Let's start chapter 9. What I'll do is I'll introduce chapter 9, then I'll leave about 15 minutes at the end for you guys to ask questions for the exam. Do you guys have any questions that you want to ask for the exam? No? If not, I'll just keep going. Let me know. Think about it.
So this one still holds pain. So there is another way to this one still because I'm just saying, this is just one leg of one here.
What we do in chapter 9
This is just like his whole, this is just one leg of it.
is we try to explain how some of the bonds that we know exist, how they form. And in this chapter, we talk about two basic theories. One's molecular orbital theory, the other is hybridization theory. They're different theories. One's not better than the other. They're different. Neither one of them is perfect, okay? They're ways of explaining how the atoms do what they do. Sometimes molecular orbital theory is the best way of explaining what happens, and sometimes hybridization theory works better. So what I'm going to do is I'm going to introduce you to both of those and tell you when to use which one. I'll let you know. In this class, well, first of all, molecular orbital theory will only apply that to diatomic molecules, just 2 atoms. It's only going to be second row, first and second row diatomics. So it's only elements in the first and second row of the periodic table, and only 2 elements in the compound. So pretty simple stuff, right? When you get into organic chemistry, then you get to apply molecular orbital theory to much more complex molecules. But lucky for you, you don't have to do the actual calculations. All you do is you get the result of a computer calculation. It gives you this picture, and that's all you need to do what you have to do. So let's talk about what it is. Remember the Schrodinger equation? Remember that there's such a thing as the Schrodinger equation? Simplest incarnation, that's it, right? Do you remember what the psi, that Greek letter, what that tells you? What that's called?
Wave function?
The wave function, right? Good. The wave function. What information does the wave function give you? Probability of finding, well, almost. You can get the probability of finding an electron if you take the wave function squared. Remember that? That's what you're saying, right? Really is this. This is review. We've seen this before. Remember, okay, talking Schrodinger's equation, wave functions, we're talking probabilities. You can't say for sure where that electron is, but with, say, a 99% probability, psi squared times delta V, which is the volume, gives us the probability of finding that electron with a 99% probability. You know, it gives us 99%, where with the 99% probability we'll find that electron. And what we talked about was how we got, from Schrodinger's equation, we got the 4 quantum numbers. Remember N, L, M sub L, and M sub S? And what the 4 quantum numbers give us is basically where the electron can be. It gives us the shapes of orbitals. That's one of the things that we get. These are atomic orbitals. Right? It's an orbital on an atom. A 1s, a 2s, a 2p, 3s, 3p, 3d, so on, right? And those have definite shapes. What we do with molecular orbital theory is take those atomic orbitals, the orbitals from the wave functions on each of the atoms, and we mix them together in the molecule. And when I say mix together, it's just, we just add them or subtract them. Right? So you don't worry, you're not going to have to do any addition or subtraction, right, of wave functions. But that's where they come from. You can picture it. I mean, that's how you calculate them. You add together the functions, the wave functions, or you subtract them, right? But what it looks like is, you know what a 1s orbital looks like. You know what a 1s orbital looks like over here. If you take 2 1s orbitals and you add them together, you get a different orbital. It's called a molecular orbital, right? These molecular orbitals, instead of being localized on an atom, they're spread out over the whole molecule. It's a molecule for the orbital. Orbital for the molecule. So these molecular orbitals, they result by combining atomic orbitals, spread out over the entire molecule, and however many atomic orbitals you mix together, you get that number of molecular orbitals as a result. I'm going to start out with the simplest molecule possible. H2+. So there's 2 protons, 1 electron. Imagine taking two hydrogen atoms, one without an electron, proton, and bring them together. Actually, let's not worry about the ion for now. Let's just start with this. Imagine taking 2 hydrogen atoms from infinitely far away and bringing them close together. And as we do that, we're going to plot the energy. Where we're going to take 0 as the energy, the relative energy of the two atoms infinitely far away, no interactions at all. We start bringing them closer and closer together. They start interacting. The orbitals start to overlap. Just a little bit. Something like that. And when they do, the energy goes down a little bit. So infinitely far away would be 0, and it's coming down a little bit. The closer they get to each other. This picture, by the way, is in your textbook. It's better than I can draw. On page 268. The energy starts going down as they get closer together. The orbitals overlap. They start sharing their electrons, right? The electrons is shared here. This is something like that. As they get closer and closer together, you get better and better overlap. The orbitals overlap, they share those electrons between the two nuclei. The energy goes down. You can think about it as, I mean, there's more to it really than this, but it's a good first step. As each of these protons, thinking about it in terms of Coulomb's law. Each proton has a positive 1 charge, each electron has a negative 1. As you get these closer and closer together, this hydrogen now starts seeing 2 electrons, right? So Coulomb's law means that Coulombic interaction is getting really negative, right? -2 times +1 instead of -1 times +1. Q1, Q2. You guys know what I'm talking about? So it's a good thing. It's lowering the energy. Same thing over here. So overall, the energy is going down. Now, you also have +1, +1, right? That repulsive interaction going on. But at least at first, that attractive Coulombic interaction brings the overall energy down. Keeps going down until it gets to a minimum. And it gets to that minimum as the atoms get closer together, then the repulsive interaction starts being more important. And it starts overcoming the attractive interaction. Does that make sense? And so the energy starts going up. And then it goes up really sharply as you get them really close together. The closer you get those two nuclei to each other, the higher the repulsive interaction. This distance right here, the distance at the minimum energy, the average bond length of the hydrogen molecule. It's about 106 picometers. We try to picture what's happening with the orbitals as this is going on. It ends up that, well, this is, let me see. We take a hydrogen 1s, actually this would be 1. hydrogen 1s orbital from each atom. That's what I'm trying to show here. And you mix them together, you get a molecular orbital that's spread out over both of the atoms. And that molecular orbital is lower in energy than either of these atomic orbitals is. It's called a sigma. That's a sigma. That's supposed to be a Greek sigma right there. Called a sigma 1s. And that comes about by adding the two orbitals. If we subtract them, you get what's called an anti-bonding molecular orbital. It looks something like this. The asterisk, the star, means anti-bonding. And in this picture here, energy is going up. So atomic orbitals here, bonding molecular orbital. Anti-bonding molecular orbital. Notice we started with 2 atomic orbitals. We ended up with 2 molecular orbitals, bonding and an anti-bonding. One's lower in energy than the atomic orbitals, one's higher in energy. Usually you show it this way. These are the atomic orbitals, these are the molecular orbitals. Energy is on the y-axis here. And what we do is, just like we did with atomic orbitals, the 1s, the 2s, the 2p, is we fill electrons, we put electrons into the 2 orbitals following the same rules as you already know about. Pauli exclusion principle, alcohol principle, Cohen's rule, right? In other words, no more than 2 electrons in a single orbital. If there's 2 electrons in the same orbital, they have to have opposite spins. If you have degenerate orbitals, the orbitals have the same energy, which you'll see a little bit later, then you put 1 electron in each before you start pairing them up. All those rules, right? That you know for the test on Wednesday, right? So in the hydrogen molecule, this hydrogen atom comes with 1 electron, as does this. And when we take these electrons and we put them into the molecular orbitals that form when these orbitals overlap, they both go down here in the bonding molecular orbital because there's room, and it's the lowest energy orbital. We were to try to make the helium molecule. Yeah. Look what happens. Same set of molecular orbitals, right? We have helium is 1s2, right? So the electrons are in 1s orbitals. Those are the orbitals that are going to overlap, going to interact. We make a 1s, a sigma 1s bonding, sigma star, 1s antibonding. How many electrons does each helium come with? 2, right? 1, 2, 1, 2. Now, following the rules, if we put these electrons into molecular orbitals, put the first 2 into here, but we still have 2 more, right? They have to go up here. So we have electrons in molecular orbitals that are lower in energy than they would be if they were in the atomic orbitals. But we also have electrons in molecular orbitals that are higher in energy than would be in the atomic orbitals. The net result is they cancel out, and this is not a stable molecule. I'll stop there. I'll pick up with that stuff next Monday. Please. I don't want to get too far into it. So.